Welcome back. Welcome back to our series lectures for protection and relay. In the past two videos or two lectures, we started the protection of a high voltage transformers. In the first lecture, we discussed the type of protection available for different type of transformers, and we divided the transformers into rating types, locations, and voltage level. We discussed the fuse characteristics required if you have a transformer protected using fuse. And also in the previous lectures, we discussed what's an instantaneous overcurrent relay. And then last lecture, we started the percentage differential relay design for a single phase transformer. We explained the concept behind the percentage differential relay for a single phase transformer. We showed the circuit analysis and we did an example as well. Please refer to the previous material for a quick revisions, because the concept of differential protection, it's exactly the same for a three-phase and a single phase. Before we go into the three-phase differential protections, I want to highlight one element regarding the inrush current. If we are going to energize a transformer, a single phase transformer, for example, without the secondary side connected to any load, I will have an inrush current. The inrush current is due because the magnetic field goes into saturations. When the magnetic field goes into saturation, the current magnitude on the primary side will go up, and the magnitude of this current will depend on the magnetizing curve of the system when it goes under saturations. This magnetizing and this current and this inrush only happen on the primary side, not on the secondary side. Also, we have one more advantage as an engineers. To resolve this issue, we have noticed this very important. Be careful, pay attention to this. Engineers noticed that the inrush current is made almost full of harmonic, while the fault current, the normal fault current, is made almost purely from a fundamental frequency. That's why it is possible for us to design a harmonic restraint relay to avoid tripping our differential relay under a rush current, and will be a false trip. I wanted to clarify this point before we go into any discussion for a three-phase differential protection. Now, let's start our three-phase protection. Three-phase transformer. The concept of differential protection is exactly the same. I need to connect a CD. This is phase A, for example. This is phase A. So I connect a CT on phase A primary, CT on phase A secondary, and I'll take him down to a differential relay. This differential relay, it's the same concept. I have to make sure that the difference between the two currents below my setting limit. One more thing I have to be careful now. For a single phase transformer, I have one CT on the primary, one CT on the secondary. There will be no phase shift. When I have three-phase transformer, pay attention. I can connect delta Y. I can change it to Y delta. I can also change it YY delta delta. If you recall, when you convert from delta Y, there will be a shift of 30 degrees. This is very important for us to take note of the 30-degree shift. Otherwise, I will have a false operation of my differential relay. I will have a false operation at the differential relay because of the 30-degree shift. That would be false because the system it's operating under rated condition, normal condition, but because during my design I didn't take it into consideration. How do I do this? The best option, I found the best option to explain this concept is to use an example. We have already discussed and studied the concept behind the codifferential protection. So let's use an example. How can we mitigate the 30-degree shift during the design of the transformer? Let's start. I've already sketched this circuit on the board, and I have a three-phase transformer. I have 34.5 kilovolt on the primary. I have 500 kilovolt on the secondary, line-to-line voltages. And I have 500 MVA three-phase transformers. I need to protect my transformers, so I need to put at the input. Where's my input of the transformer? This is my input of the transformer, this point, and this point. This is my output of the transformer. As I discussed before, I need to make sure the input and the output are the same. Otherwise, if I have an input value and I have a lot of losses before it reaches the output, that means I have a fault within the transformer. To protect my transformer, what I do is I will isolate the power for this transformer. That's the same concept we discussed before. So the first step is I need to calculate the current. How do I determine the CD? Same as we did for a single phase. All I do now is I will determine the current. Let's call this IA, this is B, and that's C. I want to find this current. How do I find this current? The equation S is equal to √3 V line I line conjugate. This is the line current. This is S. So now for me I have 500 10 to the 6 equal to √3 multiplied by 500 10 to the 3 multiplied by I conjugate line, which is IA. Now I can find IA, IB, and IC. All I have to do is a shift angle, same magnitude. So first of all, I calculate IA, IB, and IC. And then I'll determine the size of my transformer. Let's do the calculation. Let's do a quick calculation regarding this element, and then I did the calculation. I used phase A as a reference. I mean, phase A has a 0 angle. Then I added minus 120 plus 120 degree. That's what I did. So I applied this equation. Phase A is a reference. I added 120 degree for phase C minus 120 degree for phase B. And I put these other answers. 577.35 plus J0. The current IB minus 288.67 plus J500. And C minus 288.67 plus J. Sorry, this has to be minus J. This is minus J500. Now, I need to go back. I found this. Now, I go back to calculate on the primary. Has to be very careful now that this current phase will be the same inside the delta. When it goes to Y, when it goes to the line, I have to add a 30 degree, J30. I have to add a 30 degree to this system. Please remember this concept. I started from the secondary. I found the current in the secondary. Because this is a Y, That means the same current, this current, will go through the winding of the transformer. And because the transformer from winding to winding, I have no phase shift, but this is a delta. So if this current in this winding, the current in this winding, it's the same as the current in this winding from a phase point of view, then this will have a J E exponential 30. That means I have a shift angle of 30. Exponential of J 30. Remember this concept. So now, if I am going to find this ID, what do I have to do is, I have to multiply the system. I have to, this ID in here, this IA, this IA will be equal to, pay attention to IA, will be equal to 510 to the 6 divided by 34.5 10 to the 3 multiplied by root 3. I have to in here to do exponential of J30. That's very important for me to add this exponential of J30. This, because the line, this line is a reference 0. That means this here, the angle is 0. Because I'm working now on this system, I have from a delta, from a phase current in a delta to line current in a delta, I have a phase shift of 30 degrees. And that's what we've done at the beginning of this course. We spent 2 weeks, 2 lectures with a lot of examples, homework, quizzes regarding this concept. That's now where we use it. So please keep this in mind all the time. In a transformer, if I use this as a reference, that's why I have to use phase shift of 30 degrees on this side. Okay? Now I'll write down the actual numbers, and all I have to do now is I add 120 minus 120 degrees on the remaining 2, and that way I will be able to find the entire system. Is that clear? I think that's should be clear enough. All you have to do is now pay attention about the 30 degree shift. That's it for now. Now let's write down the current magnitude on every single phase. Now we wrote down the answers. So for IA, for this phase, I have 7,246.38 plus J 4,183.7. Phase B, because it's now 90 degrees, because of the 30, now it's 0 minus J, 8,367.39. For C, minus 7,246.37 plus J, 4,183.7. Great, now I find the current. Remember, what I did is, I started from the secondary. I took the secondary as a reference for current point of view, to have an angle 0. Then I went back and calculated the primary current, because now it's a delta, not a y. If it was y, I would have no issue. But now because I have a delta, I have a shift degree of 30, I have to take it into consideration. Now, the next step, the CT, I will start finding the CT ratio. Okay, how can I compensate for this 30 degree? I have to be very careful. To compensate for the 30 degrees, I connect. This is a delta. I connect the system in here, the CT system, the 3 CTs, I connect them into Y configuration. And into Y, the secondary into Y, I will connect the 3 CTs using delta configurations. So I can eliminate the 30 degree shift. Let's start now. Because this connected into Y, if anything connected into Y, the phase current and the line current is exactly the same. Because the CTs are connected on the primary side into Y connections, that means I have no problem, because the phase current that goes into the CT, it's the same as the line current. So therefore, in this case, I have the magnitude of my current. The magnitude of this current is 8,376. So that's why I can use on the primary side, on the primary side, I can use a CT of a ratio 9,000 to 5. Because the magnitude of this current, the magnitude is 8,367. That's a magnitude of the primary current, IA, IB, and IC. So I choose a CT ratio of 9,000 to 5. Okay, beautiful. Now, when I use this, the secondary current of the CT, this case, I have my CT secondary current will be equal to 8,367.39 multiplied by 5 divided by 9,000. The answer of this one will be 4.65 amps. Will be 4.65 amps. This value will be the output of the CT on the secondary. On the secondary side of the CT on the primary CT. So now the output of the primary CT will have 4.65 amps as a magnitude current. Now, let's go back to the secondary CT. Perfect. Now, what will happen to me now is, remember, this current need to go down to a relay. Let me draw this for you guys. Allow me to remove this so I can draw it. Just remember, the current is 4.65 amps. Now, this CT, get rid of this so I can draw it properly. This current in here, it's going to go to a relay, same for this current. It is going to go to a relay. Now, this current, I know it is in a magnitude, it's 4.65. I know this has to be 4.65. I need to have a similar value. I have a ferromagnitude perspective. I need to have a similar value of 4.65. This is the line current. I'm aiming to have designed a system where I have a differential of 0 under normal operation. So what I do now is I need this magnitude of the current. This magnitude must be designed for the same as this magnitude or this magnitude, depending on your direction, whichever you want to choose it. Now, this 4.65 amps, because this system we agreed is connected into delta. Look at this scenario here. These are my CTs are connected into delta. I have now this current in here that is going to go up is 4.65 amps in magnitude. In magnitude, what would be this one? This current is divided by √3. This current that comes out of here is divided by √3. So therefore, I need a CT that have a secondary output. Remember, secondary phase output, because this is a delta current. I need to design a CT now based on this system. On the secondary side, I need a secondary side CT should have a output current, phase current, should have a phase current of 4.65 divided by √3 in magnitude, which this will give us 2.68 amps. It's equal to 2.68 amps. So I need to design a CT that will give me 2.68 amps. Remember, this is my magnitude. So I need a CT. I have a CT. My input for it is 577.35. I need to get out of it on a phase 2.68 amps. So now I can determine my CT ratio. My CT ratio now will be 1000 to 5. If you do the calculation, this CT ratio will be 1000 to 5 as a CT ratio. Let me go one more time through the process that we went through. One more time. I have a three-phase transformer connected into delta Y, primary delta, secondary Y. I went into the Y conditions, and what I did is I used this condition as a reference. So IA has an angle 0, B minus 120, C plus 120. Perfect. Then I went and I calculated the line current on the delta side of the primary of the power transformers. I took into consideration the shift degree of 30. If this has an angle 0, this has an angle 0, therefore in here I will have an angle of shift angle of 30 degrees. Perfect. Then I said to eliminate the 30-degree shift, I need to swap the phenomena. So this delta, I connected the CTs, the three CTs, 1, 2, 3 into Y. So the CT on this side, they will be connected like this into Y. I connected the three CTs on this side into Y, and then I connected the three CTs on this on the secondary side of the power transformer into delta. Perfect. Now this current, I needed to match this current for the relay to give me 0 output. For the differential relay to give me 0 different current. I have to match the output line current of the primary CTs with the line current of the secondary CTs. So therefore, the secondary output of the CTs is the phase. Now, because it is connected into delta, I have my CT to give me 4.65 divided by 3 is 2.68 amps as an output. So now I need a CT ratio that if I have 577.35 will give me 2.68 amp as a phase current. Because it is delta, this reflects to a 4.68 amp magnitude into the line, which means when it goes to this CT, they will cancel each other. They were supposed to give me the difference of 0. Is that clear? Is that clear? Okay. Now one more element, and that's how I specified the CT ratio. Now when it comes to the error, the K, I have the same error for a mismatch. So same what I did in the previous video. I have to take the relay. Does it have any tap? If it has any tap, I will take it into consideration. No tap, I will take, if it says only one tap, which is 5 amps, I will do the errors and I add the errors. So mismatch error, it's the same concept as the single phase. That's one element. Number 2 element is, I will have underload tap changer. Does it have yes or no? I will eliminate it. Then I will have CT error. The type of CT that I used, of course, has an error. We already did it before. And the last one is your margin. I hope that's clear. Now, one more element before we finish. I want to show you how do we connect the CTs under this condition. Bear with me a moment. I need now to delete all this to give room. Now, in this case, I have 3 CTs. I have 3 CTs. In this case, also I have 3 CTs. How do I connect 3 CTs into Y? So all I do is I connect one side of it like this. This system will go like this, will go like that. and this is my 3 output. This is my 3 output. As you can see now, what I did is, I took the CT, remember, this is my CT, this is my CT, this is my CT. All I did is I connected this side, and I took output of this side. That's a Y connected, because that's a delta. On this side, how do I connect delta, guys? Do you remember how do you connect delta? So if I have, let's draw if I have a 3 system like this. How do I connect delta? This one will go to this one. This one will go to this one. This will go to this. If you guys remember this, so now on this side, I can go like this. Okay, on this side, I can connect this side to go to this, and on this side, so it doesn't have to be too complex. Let me make it a little bit easier for you. I will have this CT1, this CT2, this CT3. I have 1, 2, 3, 4, 5, 6. How do I connect this into series? So what I do is, it's easier for me, I sketch it like this. This is my first one, this is my second one, this is my third one. I put, this is 1, 2, 3, 4, 5, 6. Look, I connect 1 to 6, I connect 2 to 3, I connect 4 to 5, and I connect 1 to 6. Is that clear? See how I can connect them? I have to keep in mind the polarity, you know, the dot. Depending on where's my dot in here, I'll take it into consideration, but that's how I connect delta. And now I have from 1 to 6, so I have an output from here. This is one of my output. The second output from 2 and 3, this is my second output. And then between 5 and 4, which is, this is my third output. This is my line output. This is my line 1, line 2, line 3. This is line 1, line 2, line 3. And all this will go down to the restraint, will go down to a restraint, circuit. Let me show you how the restraint circuit is connected, the actual relay. So now I have one CT, one CT, one CT. All this as a Y, and in here I have one current goes in, one current goes in, one current goes like this. Perfect. In this system, I have a delta. In this system, I have a delta output. I will have a delta. This current will goes down into here. This will have something like this. This will go to the negative, which we will draw soon. The system in here will goes down to this relay. The system in here will go down to this relay. These two the system in here will go down to the negative. In here, it goes down to here. The system to the star. That's a primary side, CT1, CT2, CT3. This is connected into Y, and this will go down to CT4, CT5, CT6, and this is connected into delta, and this will go to the restraint, the relay for differential. I hope that's clear, and that's how we design a three-phase percentage differential relay. And these settings, I will set the current to a certain value. If my value exceed, if my differential, if ID exceeds my setting, it will trip. It will isolate my transformer. Before we finish this session, I wanted to recap quickly to what we did. Number one, during this lecture, we spoke about the inrush current if the actual transformer is energized with no load on the secondary. And we spoke about the inrush current, that it's purely made or almost made of harmonic, while the actual fault current is made of a purely or almost purely fundamental frequency. Then we started the three-phase transformer differential protection. There is a very important element. Number one is I need to make sure that I take into consideration the shift angle between delta and Y. When you have a delta and a Y, when you have a delta, for example, I have the phase current and the line current are shifted by 30 degrees. We discussed this in details during our phase 2 week of this course. Please refer back to the material. That's one element. It's very important for me to note. The second important element is because of delta Y, because of this 30-degree shift, I need to eliminate this 30-degree shift. How do I do this? By the CT on the delta side, I connect it into Y. The CT on the Y side, I connect it into delta. That's a second important element. The third important element, when I connect the CT into delta, I need to take into considerations the line current and the phase current magnitude. There's a √3 difference. Because I need to choose the CT ratio to give me a phase current that reflect the desirable line current. I hope that's clear. Thank you for listening, and let's now do an example together. I will post an example now on the board, and let us solve it together and discuss the result. Thank you.